In the previous videos, we had an introduction to the Google Collaboratory Service. Today, we will exploit this functionality to set up a deep learning artificial neural network and then use it for image classification. The task we are going to perform is the recognition of handwritten digits. The dataset that we will use is called MNIST. As you can see from the image, it contains the digits written by high school students and employees of the United States Census Bureau. There is a great variation on the graphic style that may also challenge human recognition. Each image is in gray shading with dimensions 28 by 28 pixels. Together with the image will come the associated correct numerical label. How big is the dataset? It contains 50,000 images for training and 10,000 images for testing. Using this dataset, we set up a multi-layer perceptron that will recognize the handwritten digits returning the number that they represent. We will use Google TensorFlow library to set up our artificial neural network in Python. Let's get started. Open your favorite web browser and reach the collab.research.google.com web address. Today we will open an external file. Go to the File menu, then open Notebook. Click on the GitHub link, type P. Mengoni GitHub TensorFlow in the search box and press Enter. Open the file 02 Image Classification MLP. Now let's check where our code is being executed. Select the Runtime menu, then change Runtime type. And check that the GPU option is selected. Click Save. This will allow the fast computations needed during training of our deep learning algorithm. Let's click Play on the first cell. When you execute the first cell, you will find a warning from Google. The Jupyter Notebook in this case is safe to be executed, so choose Run Anyway option. Better be safe when using code from the internet. Here, we define some parameters of our algorithm. The batch size defines how many images we will send to the algorithm and how many epochs of training we require. One epoch is the training on the full dataset, so our algorithm will see the full training dataset 10 times. Then we define where to find the dataset on the internet. It's on Google servers. Click Play on the next cell to import all the libraries we will need. At the end, we will print the TensorFlow library version we are using. An important note now. Execute the Hidden Visualization Utilities cell. Otherwise, you will receive a name error in the following cells. Execute the next cell. This will deal with loading and transforming the training and validation datasets. One important transformation is the flattening of our image from a square matrix 28 by 28 pixels to a flat vector with 784 positions, one for each pixel. Next cell will show our dataset. We can find the handwritten digits and their associated labels. And now we reach the core of the notebook. Next cell will take care of creating the artificial neural network. It defines it as a sequential network, with one input layer composed of 28 times 28 neurons, one for each pixel of the input image, and a dense layer containing 10 neurons, one for each possible number we can find in our dataset from 0 to 9, where each neuron is connected to all the previous layer's neurons. This layer is activated by a softmax function, thus selecting the maximum probability as a result. Then we compile the model, specifying the algorithm that will train and adjust the network weights. SGD or stochastic gradient descent. Then we define the loss function, the evaluation function that describes how bad is the algorithm at its task of recognizing images. For image classification, categorical cross-entropy is a good predictor. And the metric to verify the quality of the recognition. Accuracy is the choice for today. Then we print the number of parameters of our model. We start with 7,850. It's quite a small model. Next, we will train and validate our model. The first line defines how many steps it will take for our model to see the whole dataset. It depends on the batch size we defined at start. Then we can start the training with the fit function. We paste the training dataset to it, how many epochs of training we need. We pass the validation dataset. And finally, we require to plot the training. Once you press play, you will see two charts appearing. The one on the left will plot the loss. The loss on the training set is the blue line. The loss on the validation set is the orange line. As you can see, the loss, error, on both sets decreases with epochs. Good! On the right side, we have the accuracy chart with the blue line representing the accuracy on the training set and the orange line representing the accuracy on the validation set. As you can see, the accuracy increases with the passing of epochs. Very good! We also can see that the blue lines and orange lines go together. There is no large gap between the two. In the end, we achieve a validation accuracy 89%. Not bad at all. Let's see the predictions. Execute next cell, and we can see that our model can recognize quite well the printed digits, but fails with the handwritten ones. Can we do better? Yes, sure. Let's make our network deeper. Go back to the model definition cell. Add another layer between the input and output layers. Let's use 200 neurons and ReLU activation function, the one that has been proven to work best. Type tf.keras.layers.dense, open parenthesis, 200, comma, activation equals to ReLU, close parenthesis, and put a comma. Don't forget the alignment and the comma at the end of this line. Let's execute this cell. We will find that the model now is extremely more complex. By adding a single layer, we increase the number of parameters from 8,000 to 159,000. Let's execute the training cell again. It will take a bit more to execute. We improved the results to 92%. A bit too less for a so great increase of parameters. Now let's see what happens when we change the optimization algorithm, the AI core of deep learning. Instead of stochastic gradient descent, we will use the ADAM algorithm. Just change the model definition code by replacing SGD with ADAM. Execute this cell and execute the training. At the end, you will find that we improved the accuracy to nearly 98%. Great! But now you can see that the training accuracy is higher than the validation accuracy. This model is now overfitting the training data. It can recognize the training example very well, but still fails with the validation data. Check the predictions, and almost all the printed digits are recognized correctly. But there is still work to do for the handwritten ones. Today, we've learned how to set up a deep learning model in TensorFlow, how to train it, evaluate the accuracy, and improve the performance. Great work! That's all for today. Ciao!